part of the last lecture was starting on this example where we have 5 drugs and we want to see their effects on cholesterol level, like good cholesterol, HDL. And the idea is that we have a sample, like a bunch of people, we divide them into 5 groups, give each group one of the drugs, and measure their cholesterol level before and after, basically. And so you can set this up as a regression problem. The idea is that, so setting up it as a regression problem, I would say it's like an art. It's a little bit of, you have to think what kind of model is good for the problem and so on. So this is one way of writing it. So the idea is that so this might not necessarily be the only model, but imagine I have the Z, which is the initial HDL reading. So this variable, we have it for everyone. So this is like one covariate, one feature, one independent variable. And then I have a response, which is the final. So Y is the initial. Initial HDL reading. This is like actually Z is the initial HDL reading, and Y is the final HDL reading. And so you'd imagine like a very simple relation is that the final like HDL reading is related to the initial reading. Okay, so someone has like a high level of HDL cholesterol today, maybe after a week it's going to be still high. If they have low, it's going to be low, or maybe it's like related. So there is a simple relation. The basic relation would be that I have like Y is alpha Z maybe plus some gamma if you want, some intercept. But the most simple is like just a scale multiple of Z. Maybe just alpha is 1 or like 1.5 or something, okay? That's the simplest regression. The idea is that in this type of, at least the way that people model, or your book model this, is that the effect of the drug is like a shift of this final value. So it just brings it up or down. So you'd have some sort of a like maybe beta, what do you call it? Like beta, let's say 1. If you take drug 1, it would be like alpha Z plus beta 1. Beta 1 would be positive or negative. Okay, so if you took drug 1, and similarly, if it was like drug 2, it would be like beta 2. Okay, so it's just a constant shift relative to what it would have been if you haven't taken the drug. That's a very simple model, right? So the intercept would be proportional, basically, like determined by the drug. Okay, so if you want so if I want to write a model, let's say, if I have, so how should we write this? So if I want to write this model, so let's say there are different ways that you can write this model, right? So how should I write it compactly as a single model? So the idea is that there are these 2 variables, and then there's a categorical variable, which is what drug that particular person took. Okay, so that's like one of the 5. So I have these information, and I don't know what I should call it, but okay. So this would be like ZI, let's say ZI. This is YI, so initial HDL reading of ith person. This is the final reading of the ith person. And let's say I call it a group. So GI. So this would be in like 1, 2, 3, 4, 5, which drug the ith person took. Okay, so this would be like, if I want to write it in a scalar form, it would be like yi alpha zi yi alpha zi and so on. So like if I want to compactly write it using these groups, I can incorporate that group and I can write something like yi is equal to alpha zi plus beta gi, I from 1 to n. So this is one compact way of writing the model. It tells you compact. Okay, it tells you exactly what is going on. So my final cholesterol level depends on the initial cholesterol level by factor of alpha, and then plus the beta. But which beta is determined by the group that I was assigned. So this beta is, we have beta 1, beta 2, beta 3, beta 4, beta 5. So these are the coefficients, or like alpha, and these are the unknown parameters. And you can see GI is in 1 to 5, so it selects one of these betas. Okay, so that's one way of writing the model. And it's compact and it tells you what you're doing. So basically, the drug modulates the intercept. I could have done different. So I could have, for example, also let alpha depend on the drug level. That's also possible. I could have alpha plus something here that depends on the drug, which drug I took. So this is a simple model, right? Does it make sense? Makes sense. So this is like writing all of these. So if I is in, this is like saying if GI is equal to 1, the model will look like that. If GI is equal to 2, it's gonna look like that and so on. So instead of writing this separately for each one, write it compactly. So this is the index of the data. Okay, so far so good. So this is a linear regression problem. It's not exactly the format that we have, but you can manipulate it into a format that we have. The idea is that I can encode this information, this categorical information in different ways. So one way is to just label them 1, 2, 3, 4, 5. There's another way, which is, say machine learning is called one-hot encoding. Anyone knows one-hot encoding? What is one-hot encoding? Yes. Yes. Yeah. For multiple values for, so we have, okay, so dummy variables, that's another like good term, dummy variables. First, what was your name, by the way? Can you say louder? Hongi, okay. So can you say it again? Hongi, what dummy variables? Suppose I want to like do it row wise, not column wise. So I want to determine, so for the ith person, let's say GI is 4. How do I encode it using one-hot encoding? GI4 is equal to, so what you said is like, we have a bunch of columns, right? So what happens in each column? So what are the columns representing? Okay, so in this case, it would be like each column would be associated to one of these groups, right? So it's like group 1, group 2, all the way to group 5. So each column would be 1, and then so all the people that are in group 1 will have 1s here and 0s everywhere else. All the people in group 2 have 1s in this column and 0 everywhere else. It's easier to look at it as rows. So if I am in the ith row would have 5 elements. 2, 3, 4. So we'll have these 5 elements. So if the ith person is in group 4, what would this row be? Yes. Yeah, so 0, 0, 0, 0, 1. So this is one hot encoding because one of the entries is hot. Hot is like electricity passes through. It's like engineering. So if they're like shut their gates, so this gate is open, the rest are shut. So it's like one hot, one of the wires is hot, let's say. The others are null. So this is one way of encoding. It's very inefficient because you have 5. So these encode like nothing like informative, just that the group is 4. Right? But if I want to represent 4, I just put 1 here, 0s everywhere else. If like the ith prime, let's say this is, so this is GI equal 4. That's encoding that. If I have the ith prime person, for example, G ith prime is, let's say 1. Okay, what would that be? If GI prime is 1, what would that row look like? I'm assuming everyone, no. 1, 0, 0, 0, 0. Right, so if you look at the rows, it's just one way of encoding the categorical values. So basically you have either 1, 0, 0, 0, 0, or 0, 1, 0, 0, 0, or 0, 0, 1, 0, 0, or 0, 0, 0, 1, 0, or 0, 0, 0, 1. Okay, so you just encode these categories with this binary vector. So instead of using, so you basically map 1, 2, 3, 4 to these binary vectors, 0, 0, 0, 1, 2, 3, 4, 5. Right? So this is an encoding. It's an encoding because it just encodes the same information, but in a different format. Okay, there are different kind of encodings. You could have, so if you take like in electrical engineering or information theory, this is one way of coding the information. There are many different ways of coding, okay? So just a little bit of information theory. So for example, if I flip one of the entries here, I mean, one idea is like if I want to like pass it through like a noisy channel, how do I encode so that if one bit gets like flipped, I can still tell which thing like I sent. So that's like a whole different sort of course on how to do coding. But the idea is that I can code categorical values in different ways. The way we code it here on hot encoding is useful. We don't have any noise here, so we assume that we just observe these. The way we encode it is useful for like statistical purposes. You could encode to different properties. You could encode to like maximize your recovery under a noisy channel. Or like you could encode to simplify something else. We'll talk about that a little bit more. So I have this encoding, so map these to that. So now you can think of each, once I plugged in, encode every one of these variables like this, I can put them in a matrix as rows of a matrix. I get a design matrix. Okay, so I get something like, maybe the first guy is in the group 1, the second guy is in group 2, the third guy is group 2, group 2, group 3, group 1, group 4, group 5, and then group 4. The rest is 0. Okay, so I get some sort of a matrix in which the rest are 0. Right? I'm not going to show. But that would give you a matrix with 5 columns. So I can call them x1, x2, x3, x4, x5. And then I also add 1 column, which is z. Now I have a nice design matrix. I can think of each one of these as was pointed out, dummy variable. So each one of the x1 up to x5, I can call a dummy variable. That's one way people refer to these. These are variables that sometimes dummy variables, sometimes indicator variables. Indicator. So they create these artificial variables. I don't know why they call it dummy, maybe artificial. But indicator means like there's just 1 and 0. So they indicate. So this is the indicator of being in group 1. So if I look at this column, I can immediately know which people are in group 1. I look at this, it indicates which people are in group 2. So it's indicator of the group. Dummy variable for that. But these would provide me with artificial variables that I can now do regression. Okay, so that's one way to incorporate categorical variable into regression. Categorical levels are not numerical, but I can introduce dummy variables. Okay, one way to incorporate categorical variables. We call variables in regression. I can make them 0, 1 dummy variables, and now I have a usual covariance. I just created that 5 covariance, extra covariance. Okay. So now I want to write this model as a regression with this design matrix. So this would be my design matrix. This whole thing, we're going to call it X, will be n by 6. It's going to be our design matrix. I want to write that model as y equal x beta plus epsilon. Because there's noise here as well. Okay, how can I write that? So this model I'm gonna write this. Rewrite as this guy. So where X is that matrix above. So how can we do this? So beta here would be alpha, beta 1, beta 2. Alpha, beta 1, beta 2, beta 5. This X is Z here, X1, X5. Actually, they don't have to do anything. Just writing it like this would work. Okay. If I just multiply this X by that beta, yes.
Z would be power 1?
No. Z is the initial HDL level for everyone. It's not the intercept, it's just part of the data. The intercept here is encoded like this. Okay, so the intercept, basically the model is like yi is alpha z plus beta.
So when the model comes back alpha
Alpha would be what?
When we actually run the model, alpha would be the projected intercept.
It's not the intercept. No. The intercepts are actually these guys. So you can see ZI is like, ZI would be just the variable, like genuine HDL level. So it's like writing y is beta 0 plus beta 1 z. So that's the z. The intercept is this guy. In our case, the intercepts are these, right? If you want to write it. I'm going to reorder so that you can see it's like this goes here, this goes there. Now it's the intercept, because usually I write the intercept first, right? So beta is a parameter. So it's like a constant shift. Alpha is multiplied by this. This is a genuine variable. So this looks like usual, right? Simple.
Which group you're in, get the intercept.
Different intercept.
Multiplication factor for the initial level?
Yes. So if you want to read this, if I look at one group, I got an intercept plus alpha times that, right? If I look at different group, I get a different intercept but alpha plus alpha zi. So this part is the same. So within each group, you're running a simple regression, but in each group, the intercept is a different parameter. So what you're doing is you're running basically multiple regressions, one within each group, but you want the same parameter alpha. So you're not going to separately fit. So you could separately fit simple linear regression to each group, but then both these and these would vary. Okay, both alpha and beta would change. Because if I just fit a simple linear regression to group one, I'm just going to have yi is like some beta plus some alpha times zi for that group. For a different group, I have a different beta plus a different alpha times zi. That's what happens if you like run a full simple linear regression. What we're doing is we're saying everyone has the same alpha, but the intercept changes as a function of the group. Okay, so the effect of the drug is encoded in the intercept of the model.
On the slide when you had like y equals the equation that you got,
yes.
At that point, x1 when you plug that in.
So that one is exactly this. That's what I'm trying to get at. Oh. So this model, I shouldn't have started with this. This model is exactly this model. How is it exactly this model? Here I'm encoding the variables using a categorical GI. If you encode this using a dummy variable, just different encoding, if you write it this way, you can write the model like this, or if you want, you can, it's equivalent to saying y is equal to alpha z plus beta 1 x1 up to beta 5 x5.
And all of the ones from beta 1 x with the beta 5 x5, those would all be constant.
Can you say that again?
So all of those would be constant, because we can't really plug in a value for x. We can think that it was a variable.
No, x at this point is
either 1 or 0. So you only take the one that you want.
Yeah, so it's either, so if you imagine what happens in this model, so if this is like a vector version, so for each row basically would have, so each row would be yi is equal to alpha zi plus beta x1I plus beta 2 xi2 dot 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 beta, write it a little bit bigger, plus beta 2 xi, sorry, x 2i plus beta 5 x5. Yeah, I should write it different. Okay, you want to be a little bit more, I1, I2, xi5. So this x, yeah, it's a little bit tricky. So xj is the jth column, and no. So the jth column is, so I'm gonna write, so let's say the third column, but the second column, that's the second column. So how many are 0 or 1 depends on how many are in group 2. So these are the columns. So xi, so okay, so x is like xij. Okay, so this is saying this xij encodes whether the ith guy is a group J. So if I is the ith sample, like the ith person is a group J, it's going to be 1, otherwise 0. Okay. If I look at xj the way I wrote it, this just is the J column of this. Just if you look at it, it just tells you the rotation of the y tells you which persons are in group.
So in that whole column, you'd have how many people, the number of people in that group.
Great, yes, yes.
But then you have y as the row, right?
No, this is the column version. So yeah, so this is an entire column. So when I write things like this, these are column wise, right? So so this is like a column. This is a column, right? This is a column. And so if I want to look at the rows, if I write the ith row, so the ith row of this would be yi, the ith row of this would be zi, the ith row of this would be xi1.
Right,
but now in this case, so if you just fix I,
right, then 4 of those are going to be 0.
4 of them are going to be 0, yes, that's correct. In this equation, for each fixed I, exactly one of these terms would be non-zero, right? And so for example, if the ith guy, if gi is equal to 4, then xi1 would be 0. xi1 is equal to xi2 is equal to xi3 is equal to xi5 is equal to 0, and xi4 would be 1, right? So then, I mean, these two would give me that yi is equal to alpha zi plus beta 4 xi4, right? But it's 1, so I get this, right? And this is what exactly what I want, because this is just equivalent to saying yi is equal to alpha zi plus beta gi. So if you do it like the gi equal to 3, only the third like covariate there is 1, the rest are 0, so you get alpha zi plus beta 3. And 3 is just gi. So you always get this version. So only one of these elements, only one of these pairs will be active. Okay. So you have to like think a little bit about it. For each row, basically, one of the xi is active. For each column, there could be multiple active, and those are like indicate like exactly how many people in that group will be active. Okay, so you can see like in each row there's just exactly one. In each column, it could be multiple ones, depending how many people are in that group. But the main point is this model is, so this is equivalent to that model. This is equivalent to that. Okay, these two models are the same, just different encodings of the category. I just want to like get that point across so that it's clear. I like this version because it's much easier to understand, but it's harder to actually like implement because you want it, like if you have like LM command, this is not the standard form, but if you like encode things like this is not a standard regression problem. You can just plug in X, Y, out comes beta. Conceptually, this is easier to understand because it just exactly shows that there are two variables, two real information, pieces of information, one categorical, one numerical. This one, like artificially gives you like 6 covariates, but really the information is not 6 genuine covariates. Perhaps that's why it's called, or they're called dummy variables. Okay, questions? Spend a lot of time discussing this, but I hope it's clear, right? So you could have, for example, encoded different models. So you could have different models. I could have, for example, assumed that the alpha also depends on GI. That would be this model. This is a different model. Then you'd have to also like take into account these different alphas. So it would be good to try. I could have something like alpha 0 plus alpha GI ZI. Sorry. ZI plus beta GI. So there is this basic alpha 0, but then it's modulated with the groups times ZI plus beta GI. There are different ways that you could like play with these. Multiple ways of doing it. But for now, so you'd see some of this in the homework. It depends on what you want to do. If you believe that this coefficient also is affected by the drag or not, because the drag just shift there's a constant shift. So this depends on what your assumptions are or what kind of model you want to have. So so let me maybe more complicated model. More complex model is yi is equal to alpha gi zi plus beta gi. So this model, one of these models is strictly a super model, or one is submodel of the other. One is contained in the other. So in this model, you have alpha 1 up to alpha 5, and then beta 1 up to beta 5. In this model, you just have alpha and beta 1 up to beta 5. So which model is included in the other model? Submodel. The first one, yeah, the first one is a submodel of the other one. How do we know, or how can we?
The second one is you're setting alpha 1 equal to other way.
Great. So if I enforce a constraint like we had been doing, if I set all the alphas equal to each other and equal to some basic alpha, so this model reduces to that. So I can, for example, do an F-test testing between these two models. So if I start from this, I can test whether it's good to set all the alphas equal or not. Okay, if I set all the alphas equal, I get this model. So I fit both models, and then I do an F-test, decide which one I want to prefer. Okay. In this problem, we start with this and go one step below. Okay, so what we're actually doing is we're gonna try something like, so let's say I have yi this was the more complicated model. From this is the middle ground that your book uses, zi plus beta gi. There is another one which is like alpha zi plus beta, right? So reduction, it's another reduction. If I set all the betas equal to each other, I get this model. So this model is a strict submodel of this. This model is a strict submodel of that. So if I set some of the alphas equal, like all the alphas equal, I get this. If I set all the betas equal, I get this. So this model is a bit like the bottom of the hierarchy. So what we're gonna do is like call this, we call this full model, we call this like the reduced model, let's say. You could have started from this as a full model, tested this, or test this against that, or whenever you have submodel relation, you can do an F-test. But here you're gonna start from this, and then test, for example, this. If I believe this, then testing whether all the drugs have the same effect would be just equivalent to setting all these betas equal to each other. So, and so assume M and test whether beta 1 is equal to beta 2 is equal to beta 5. That would be my null. So in that case, I can set all of them equal to beta. I get this reduced model. This reduced model is just a simple linear regression. So you fit this reduced model, you fit the full model, and then you compare the SSEs, you have your S statistic. Right, that's what we are trying to do. I just wanted to mention that it's not the only model, so you have a more complicated model. Okay, just focus on this. Start from this, let's say. Why we started from this? That's the art part. Now I can try to test this. So this test is testing whether all the drugs have the same effect, because the only part of the effect is like in the intercept. If I test whether all the intercepts are the same, it's like testing whether all the drugs have the same effect. So if I want to do this test, so any questions first? How do we do this test? So I'm gonna fit. So fit both models. So I get SSE of M and SSE of M reduced. So I can calculate the some residual sum of squares or SSEs. So then how do I perform the test? Can you tell me how to write down the F test statistic? F hat would be the additional sum of squares, which is the difference of this minus the SSE of M reduced, divided by the degrees of freedom, and divided by something. So what is the degrees of freedom here? 5. So in general, what is it? Q. What is Q? Number of constraints. So how many, like number of linearly independent constraints? How many linearly independent constraints we have? So we can like beta 1 equal to beta 2, beta 2 is equal to beta 3, beta 3 is equal to beta 4, beta 4 is equal to beta 5. 4. So we have 4. So how about the denominator? So we compare to the SSE of the full model. So SSE of M divided by, this would be N minus D. So N here in our case is 50, right? So 50 minus the number of parameters of the full model. How many parameters we have in the full model? Full model is this one, or this one basically. Just count the number of parameters. 6. Okay. 6. And so this would be under null, it would be an F, has an F distribution with 4 and 44 degrees of freedom. Okay, so so that's basically the idea. So once you, in our case, in this case, I'm setting it to equal to gamma, but you set all of them equal to gamma. Let me see if I have the, just maybe look at this. Is it okay? Or remember this? I just have to fit the reduced and the full model. So you do this for the reduced model. I'm using M1. So that in this case, it would be 29. 30 here is going to be 25. 50. The additional sum of squares would be the difference, which is like in this case, or extra sum of squares, 427. So this divided by Q, which is 4. And then E squared is the, so this is like the SSE of, oh, okay, I made a mistake here. So no one mentioned. What was the mistake? The mistake was the order here. SSE, M reduced has a bigger SSE. So M is the bigger model, will have a smaller SSE. So the smaller, the submodel will have a bigger SSE, if you remember. So SSE M reduced first, this is like the M reduced. This is SSE of M. And so this is like the numerator, the denominator is just SSE of M divided by 44. So it has, you should have like 4 and 44 degrees of freedom. And so in this case, you get 1.87 compared to the tails of this F. So the probability that this is bigger than 1.87 is 0.13, which is the p-value. The p-value is bigger than the usual value. Not, you do not reject it, it's not. Yes.
Wait, so Q is 4 because you mean by 4 linear.
So what do we mean by 4 linear constraints?
Number of equations that you create that way, isn't it?
The number of linearly independent equations that you need to write down Yes.
That was like the B1 equals B2, B1 equals B3, B1 equals B3.
Yes. Therefore, yes. So you need at least 4 to make all the parameters. And if you add more, it would be redundant. You can say beta 5 is equal to beta 1, but that would be redundant. Okay, so how do we fit this? This one is simple linear regression. This one, you can just do this. Do the dummy variables. You have capital X, X transpose, X inverse, X transpose Y. That would be your beta. You plug in. So just usual regression with this design matrix. Okay? Yes.
So for the reduced model, we just assume that all the beta.
So yes, no, not equal to 0. Not equal to 0. Yes, that's the hypothesis that we want to test. So I want to test this hypothesis. So the question is whether the drugs have the same effect. If that's the case, and your original model is this M, then the hypothesis you can encode like that. Okay. If they have the same effect or not is equivalent to whether the betas are all the same or not. That's like how you can, depends on what question you want to ask. This is like the first question that we ask. Okay. We can ask a different question whether, so in this case, we didn't reject. So I hope p-value is sort of clear for people. We talked about p-values. P-value in this case, again, p-value is a random, it's better to think of it as a random variable. It happens to have this value in this case. And the way you calculate it is just, is this extreme under the null distribution? So you have the F distribution. So you want to see how far in the tail you are. So in this case, it's like 1.87. And the mass above it is like 0.13. So this is not that extreme. Like there's a 13% chance of observing something like that. Usually you reject if the chance is below 5%, yeah.
So for the design matrix for the reduced model, you would have that A matrix, and then you would have, and then you would
so for the design matrix for the reduced model, so what would be the design matrix for the reduced model?
would be the A matrix.
A? No,
You
no.
find it,
Yes.
not the A matrix?
No. So A is the indirect way of doing it. So A beta is equal to 0. You usually write this as Z gamma. And then you plug in Z gamma.
So it would be X.
A XZ, yes. Yes.
And Z, then you would say as.
Z you have to write so that you have the
So that would be alpha and then beta beta all the way down. Because they're all the same.
So what would be Z in this case? So beta is alpha beta 1 up to beta 5. So once I have set all the betas equal, let's say I'll set all the betas equal to gamma, right? So this would be alpha gamma all the way to gamma. This is actually bad notation because gamma is, this gamma is a different gamma. So alpha, I'm going to set it to equal to beta, beta all the way to beta. Then I want something here such that when I multiply by alpha, beta, the new parameters are alpha and beta. So what would that Z be? So I need something which is like 6 by 2. Because this is 6-dimensional. The number of new parameters is 2. So I want to map 2 to 6. So that Z would be, beta would be something times alpha and beta. So 6 by 2. The first one is going to be alpha. So it will be 1, 0. The second one would be beta. So it will be 0, 1. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1.
Do X times that, and then that will give you something that will
Yeah.
to covariance.
Yes.
Run the regression model.
Yes. 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 You could do it like that's the hard way of doing it, but good. That's
Then how do you multiply
the easier way. Sorry. Okay. The easier way is just set all the betas equal, as I did. So you don't have to worry about the. So this is a very good exercise actually for you. In this case, it's much easier to see what. It's much easier to see what the reduced model is from this formulation. Once I set all these equal, so all the betas would be beta. So the reduced model is just a simple regression. So the design matrix here would be, depends on how you write it, but if I have alpha and beta, what would be the design matrix here? Simple linear regression. No, it would be just one. And then here would be, sorry. If I do alpha, it would be like Z here and then one. It's just, yeah, this is equivalent to saying yi is equal to, this model is just y is alpha z plus beta 1 plus epsilon. Usual linear regression, like usual simple regression. This is the intercept column, just happens to be on the other side. And then z is just your polarity. Just you have the column of constant 1 and then z. So in this case, if you look at this version, you immediately get this version and you immediately see the design matrix. You don't have to do that calculation. But if you want to do it, is this sort of clear? So if you want to do it, you do, so yeah, it's a little bit like going to be messy if you look at it later. So that's one way. That calculation that we did, beta is equal to 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. This is bad notation. I'm gonna write it as like alpha and let's write it as QC. So there's a different notation, not confused with beta. So this is beta. This is the constant. 1 more 0, yes. 0, 1. So that would be my Z, that would be my gamma. So what is X here? X is gonna be like Z, and then this X1 up to X5, these dummy variables. So then I would have X times Z, which is gonna be that X times this 1, 0, 0, 1, all the way to 0, 1. Once you multiply this out, so this is like n by 6, 6 by 1. What happens is that you're gonna sum all these columns. Once you sum all these columns, if you recall what this is doing, it's like, again, like a little bit of linear algebra. When you multiply from this side, this vector tells you the coefficients of the column visits. So you get a linear combination of the columns with these coefficients. So only you get the first column, the rest are 0. So the first column of the result would be just Z. And then you get the second column, which is just a linear combination of the columns with these coefficients. Right, so this is like how you do matrix multiplication from the other side. So I have these, why is it not different color? So when I form the second column here, it's just going to be 0 times this, 1 times this, 1 times this, 1 times all of it. Okay. So you add up all the columns. So this column would be, this column turns out to be X1 plus X2 all the way to X5. If you imagine what these are, once you sum all these columns, because you have exactly one row in each, one in each row, when you sum the columns, you get 1, 1, 1, 1, 1, 1. So you have the matrix of all ones. Okay, so this turns out to be equal to 1, so you get back this idea. So this is the hard way of doing it, yes.
When you do the whole thing at the end to find the finite value, you would just do XC, X gamma, and that would be the
yes.
you had.
Yes, yes, yes. Or yeah, in this case, if I want to like call it, I'm going to write it as, to be consistent, this is going to be alpha and QC. This model is going to be QC. I'm setting all of them equal to QC. To be just a new variable so that it's not confused. So you basically fit this model. or if you want xz gamma, gamma would be your new parameter. And then the fitted values would be xz times gamma hat. But in this case, you don't have to do the hard way, just the usual.
And then you have to find the residual. Then now your Y matrix won't be the right dimension.
Y is the same every time. Y is not going to change.
Oh, that's what, because if you do xz times gamma, it will still create 50 values, and then you can.
Yes, so you get Y is equal to xz gamma plus epsilon. This side is always n. This used to be d. This is like d, now d minus q. So in the end, this thing is going to be n by d minus q. Gamma would be d minus q. In our case, d is 6. Yeah, q is 4. D minus q would be 2. Still, you have 2, so you get n by 2. Y remains n by 1. Yes. Yes, yes, yes. Everything works. It's just the usual regression with a new set of parameters and a new set of providers. Okay. Now you have a very good understanding of how to do it. The hard way, the easy way, the middle ground. Okay. So if you really want to make your life harder, you can do it that way. It's a more general way, right? So if I give you a general set of conditions, A beta equal to 0, if you can make the dual version, which is beta is equal to Z gamma, then you plug the Z gamma. It's like a standard way. In a lot of the examples that we do, I shouldn't say a lot, but like the majority or most of the examples in the book, once you enforce the constraints, the reduced model is very simple to see if you have looked at the model correctly. Okay, in this version, this version, as I mentioned, it's easy to see what this reduced model is. You just set all the beta equal to the CQC, this model just reduces to that. You don't have to worry about the Z matrix and that. But if you want, you could do the more general approach. Sounds good? Good question. So this helped. I was going to gloss over this part, but now you have different ways of doing it. So reduced model is another regression model with a new set of parameters, the same sample size n. So you just have to figure out the new design matrix, the new variables. You just fit it as a usual regression model. The full model is in this case, the full model is actually more difficult to fit because this form is not natural. You have to go to this version. But the reduced model is really simple. Questions? Now I want to do another test in this model. This test is going to test whether the drugs have. So far we see that they don't have differences. Now you want to test whether they actually have any effect at all on HDL or not. So if I want to do that, what is the further reduced model? So if I want to test whether they have any effect at all or not. Yes. Yeah, you set them all equal to 0. So now let's say, second question, first question 1. Question 2, whether they have any effect at all. So this is for question 1. Question 2 would be like H0 is beta 0 is equal to beta 2 all the way to beta 5 is equal to 0. The effect of this is that I'm going to go from one level down. So I get yi is equal to alpha. Zi, this QC I said is equal to 0. Okay, so this is a new model. This is at the bottom of the hierarchy. So this is a submodel of the previous model, which is a submodel of the previous model, which is a submodel of the one that we actually didn't consider. So you can see there is this hierarchy of models. It gets simpler and simpler and simpler and can test. So now that hypothesis is testing this model. Setting all these equal to 0 is equal to setting it equal to 0. So you can actually see that this model, this hypothesis, gives you a model which is a submodel of the model that you get in the previous hypothesis, which itself is a submodel one that you get from this stuff. Okay, so you see this nested business. But in any case, what we do is, what I can do, for example, is I can test this against that, but your book tests this against the original one. So this is the art part and the tricky part. So you can do different things. So I tested this against this null, and I did not reject. So now my null is this. I can now test this against that. This is rather simple. I can do actually a t-test here, or you could do an f-test. The t-test and f-test for a single variable will be the same. We haven't talked about this, but I can, for example, fit this regression and test whether this coefficient is 0 or not. If this coefficient is 0, I get this. So I can do this test by t-test. But your book wants to do an f-test, a genuine f-test. So what it does is that you compare this to the original model. Okay, at this point, it's just up to you what you want to do, or up to whoever asks you the question on the exam to do which test. But they're freedom. So as a statistician later in life, it's up to you what you want to do. But I hope you understand. So there are different models. You can do different tests. So what we are going to do is like start from this. You have to first figure out what is the base model, like the background model. The background model for us is still going to be this. Now I'm going to test this hypothesis under this model, which would be equivalent to going from this to this. I'm going to call this M. Yeah, so let's call this M1. That's why it's good to call this M1. I'm going to call this M2. So this was M1. Now for question 2, I would have M2. I'm going to do the F nu. F hat would be SSE of M2 minus the base model is still M. I want to do that. And then divided by something. The denominator is not going to change because that's the base model is still the same. So 15 minus 6. So how many constraints do we have relative to the base model, which is M in this case, if I want to do this? 5. So you can see like I have to set all the betas equal to 0. So this would be 5. And under H naught would be 5 and 45. Okay, so what you do is you fit the new model, which is just a very simple regression, this model. And this is M2. The SSE is going to be big. So you can see this is the SSE of M1. So SSE of M1 is 2,900, about 2,900. The SSE of M2 is even bigger because it's like below M1. Right, so you have M1 is a submodel of M2 is a submodel of M. So the SSE of M1 is going to be bigger than or equal to SSE of M2. Sorry, the other way around. M2 is a submodel of M1. So M2, SSE of M2 is going to be bigger than SSE of M1. It's going to be bigger than SSE of M. So in this case, this is going to be 3,410. This is 2,930. This is 2,505. So it matches. So you compute this. The difference with the original model SSE would be 900 divided by 5. The denominator is the same. 3.8 compared with the quantiles of F5 and 44. And in this case, you do not reject. So p-value turns out to be 0.02. Compared with the arbitrary like threshold, it's fine. So we do not reject H naught. Sorry, actually, we reject H naught. So we favor M over M2. So it's a little bit tricky. So you favor M over M2. So if you compare M and M2, you favor M, right? If you compare M and M1, you favor M1, okay? So maybe we should go with M1, right? Then you can also do another test M1 and M2. Hopefully you favor M1. And I forgot what the answer would be, but as a test, as an exercise, do compare M1 and take this M1 as the base model, constrain it by setting PC equal to 0, and you get this model. You can do an F test there. You can also do a T test. It would be equivalent. I might actually have it here. Okay, compare M1 and M2. I don't know if actually the answer is correct, but do this as an exercise, okay? It may be like numerically correct, but hopefully you favor M1 over M2. So things would be consistent. You could do like a bunch of tests, and it could potentially in practice be inconsistent. So you could, for example, test M against M2. We did this, we favored M. Test M against M1, we favored M1. Then you do M1, M2, maybe you favor M2, then it would be inconsistent. But hopefully if you do it, you favor M1, then everything points to M1, so we'll stay with M1. Okay. So once you understand this M test, like F test, it's a very interesting device that you can use to compare models. Just think of F test as a way to compare different nested models. Okay. And as an exercise, if you want, do an F test in here and do a T test in M1 and for TC equal to 0 and show that they're the same. So you should get exactly the same p-value. So the F statistic would be basically the T statistic is squared in that case. So the square of the T statistic would be the F statistic. This is a good exercise which you can try. Questions? Yes.
So in this case, the only covariate we care about is alpha because the other one.
Yes, yes.
So the Q will be 1.
No, depends on what you want. Yeah, so it depends what the base model is. So yes, M1 and M2 would be 1, yes. So in this case, you have 2 covariates in the original model and 1 constraint, which is 1. So Q would be 1 in this case.
So what about the bigger for the denominator?
So what do you think?
What?
The denominator would be N minus. It would be big. So N minus the number of parameters of the full model, which is 2 in this case. So we 50 minus 2. I think this is wrong then. So 50 minus, that's why I remember now this is wrong. So it should be 50 minus 2. Okay, and that would be 1. And then you do the calculation, most likely the result would flip. And you did inconsistent. So the statistics are inconsistent, and so you run into like an error. That could happen. If you start doing a lot of tests, then that's the issue. So the issue with multiple testing is this, yes.
So this is an F test, whereas you said that you could do a T test for the other one.
For this problem, you can do a T test.
So then when we do the F test, will we substitute the 6 or is that not true?
The T test, there is like a little bit different. T test, if you recall, well, how do you do the T test?
So it makes sense to me why we're doing 50 minus 2 for doing the T test, but why we also doing that for the F test?
No, 6 is wrong. That's the thing. In this problem, there's no 6.
Oh, so it should just be 1 and 2.
Yes. Yes, 1 and 50 minus 2 in this case.
The base one is only all parameters.
You just have 2 parameters, yes. So 50, it should be like 48. So I should correct this. So just, this is not correct. This is not correct. So it should fix it. The t-test would be just fit the regression and then do a t-test for C equals 0. Just done this before, right? And do it as an exercise, it should give you the exact same p-value. The statistics also you can compare. If you compare, calculate the t statistic, square it, it should give you the f statistic. Technical points I'm gonna leave. Yeah, there's this slide that you could go over in algebra and statistics that you translate between. So subspaces or submodels. Fitting is projection, residual sum squares are unexplained variation. There's like a nice way of comparing it. I've mentioned this before. Any questions? So let's do a little bit more. I'm gonna next set of slides. Now you know that it's just everything is gonna be simple. I'm gonna be very quick. So ANOVA, the usual thing that you have probably seen, sometimes called ANOVA, in your book called ANOVA. ANOVA, like you can call every one of the things that we did ANOVA. It's like a decomposition of variance. But this particular ANOVA, I'm not gonna insist on the name, but if you wanna test the strength of linear relation in regression, This is probably the F-test that you have seen. If I fit a regression model and I want to see if there's any effect of the covariance, I can just test whether all the data is equal to 0. I would have the base model, which is the intercept only model. If you want to compare the full model to the intercept only model, that's the traditional F-test that you have probably seen. So sometimes they ask you to test for the significance of the linear relation. Okay, that would be this test. So in this case, all the beta, like you have P constraints, all of them equal to 0. And the full model would be like, I'm calling it MP, the simple model, I'm calling it M naught. You just compare the two. In this case, when you fit this model, if you remember what beta hat 0 would be in the simple model. We talked about this. If you just have the intercept and you fit it, beta hat would be y bar. Okay, so if you fit the intercept only model, this would be y bar. So the SSE for the simple model would be y minus beta hat times 1. These are the fitted values. So with y I minus beta hat 0, y minus y bar squared. So that's called SST. Sum of squares total. So SST is really the SSE of the simple model. So your test would be like SST minus SSE divided by P divided by SSE divided by N minus P plus 1. Under null would have, so the SSE here is the SSE of the full model, the regression model, would be F. I'm going to call this D. N minus D. D is going to be P plus 1. This would be P and N minus D. There's just a special case of this, and then this difference is called SSR. The additional sum of squares is called SSR. So you'd have SST is equal to SSE plus SSR. That's the Pythagorean theorem that we had. In this case, that they have these different names. Okay, so regression sum of squares. So SSR is interpreted as how much variability explained by the full model or by the covariance over the simple model. And then you write these things into an ANOVA table. So it's just the summary of the model. So model has P degrees of freedom. Residual sum of squares has N minus P minus 1 degrees of freedom. The total, this is the SST degrees of freedom, which is the sum of the two. We don't use the N minus 1, but that's the degrees of freedom of SST. SSR, SSE, you can calculate the different formulas, you can just play with it. Then you also sometimes write MSR and MSE. So MSE would be SSE divided by the degrees of freedom. So this thing is called MSE, mean squared error. MSE, this is called MSR, right? Mean squared regression. So when you divide it. And then so the F-test would be just MSR divided by MSE. So you see these tables. It's just progressively computed. You don't have to write it this way. It's just traditionally they did it. And there are these different formulas for the SSR. And it's good and it's really sense. Try to do it. We're almost out of time. Next time we'll come back talk about, so you know R squared, in this case, SSR divided by SST would be R squared. And if you look at that identity that we had, would be 1 minus SSE divided by SST. Because of that identity, it's going to be between 0 and 1. And so when it's close to 1, you have a very good fit. When it's close to 0, you have a bad fit. And I'm going to come back and talk a little bit more about this. And we'll continue. Thank you very much.